Traditional technical analysis relies on experience and intuition, while machine learning depends on data and algorithms. What happens when these two worlds collide? Today's strategy transforms traditional indicators into machine learning features. It uses the KNN algorithm for scientific predictions, giving every trading decision solid data science backing. Hello everyone, welcome to the Inventor Strategy Selection channel. This channel focuses on discovering the most forward-thinking quantitative strategies in the crypto space. The KNN algorithm is based on the core idea of you become like those you associate with. When predicting new samples, it finds the most similar cases in historical data for weighted prediction. This strategy applies KNN to financial time series data, using sliding time windows to dynamically maintain fixed-length historical training sets. This ensures the algorithm always bases predictions on the most recent market behavior patterns, effectively adapting to market structure changes over time. The strategy extracts 7 technical indicators: price momentum, RSI, volume ratio, volatility, trend strength, MACD difference, and Bollinger Band position. After standardization, these form a 7-dimensional feature space as market state vectors for each time point. During trading, the algorithm calculates real-time similarity between current market state and historical samples, selects the most similar historical points, and uses inverse distance weighting to predict based on these historical cases up or down results. The more similar the features, the greater the weight in prediction. This dynamic updating mechanism lets the strategy continuously learn the market's latest evolution patterns. Compared to traditional static weight methods, it achieves true adaptive time series modeling. The parameter design reflects KNN algorithm's core concepts and risk control philosophy. The K value determines how many historical similar cases the algorithm considers, a key parameter affecting prediction stability and sensitivity. Historical lookback period controls the algorithm's memory depth, providing sufficient sample space for pattern recognition. Feature calculation period affects technical indicator response speed, while standardization period balances feature stability with timeliness. Prediction threshold serves as the first line of risk control, generating trading signals only when the algorithm is sufficiently confident. Stop loss and take profit ratios follow classic risk management principles, providing clear exit mechanisms for the strategy. Proper configuration of these parameters is crucial for maintaining stable performance across different market environments. Feature engineering is the core technical component of this strategy. First, we define a standardization function using z-score method to convert all features to the same scale, a basic requirement for machine learning algorithms. 7 raw features each have their strengths. Price momentum captures price change velocity. RSI identifies overbought or oversold conditions. Volume ratio reflects market participation changes. Volatility measures price stability. Trend strength quantifies trend direction through dual moving average differences. MACD difference provides momentum information. Bollinger position shows relative price location. The key innovation is standardizing all raw features, eliminating scale differences between different indicators. This allows the algorithm to fairly weigh each feature's importance. This processing ensures accurate distance calculations, something traditional multi-indicator combinations cannot achieve with such precision. Signal generation starts with establishing the machine learning training framework. Target label definition uses the most intuitive up-bot-down binary classification method, simplifying complex price changes into 0 and 1 judgments. This simplification loses some detail but greatly improves algorithm interpretability and execution efficiency. Historical sample management is KNN algorithm's infrastructure, using sliding windows to ensure the algorithm always learns based on latest market patterns. When historical samples reach the set limit, the system automatically removes the oldest data. This dynamic update mechanism allows the algorithm to adapt to market structure changes. Feature vector construction combines 7 standardized indicators into unified data structure, laying foundation for subsequent similarity calculations. Similarity calculation is KNN algorithm's core component, determining historical pattern matching accuracy. Euclidean distance as a classic multidimensional space distance measure accurately reflects similarity between current and historical market states in 7-dimensional feature space. Smaller distance means 2 market states are more similar in technical indicator combinations, making their historical trends more valuable for reference. The K nearest neighbor selection process uses sequential screening, finding minimum distance each time, then resetting that distance to maximum value. This avoids selecting the same sample repeatedly, ensuring the chosen K-samples are truly nearest neighbors. This strict screening mechanism guarantees prediction quality, avoiding interference from duplicate samples. The entire process demonstrates machine learning's transformation from data to knowledge. Weighted prediction is the essence of KNN algorithm, reflecting how distance affects prediction weight. Inverse distance weighting ensures more similar historical cases carry greater weight in final prediction, more scientific than simple averaging. The 0.001 offset in weight calculation prevents numerical anomalies from zero distance, showing attention to engineering details. Final prediction value between 0 and 1 represents upward probability. This probabilistic output is more flexible than traditional indicator absolute signals. When prediction probability exceeds set threshold, trading signals are generated. This threshold processing converts probability prediction into concrete trading decisions, completing the full cycle from data analysis to trade execution. The entire prediction process showcases typical data-driven decision-making in modern quantitative trading. Strategy execution, logic reflects standardized processes in modern quantitative trading. Risk management calculations are based on position average price rather than entry price, more accurate for partial position building or scaling in scenarios. Entry conditions are set for signal triggers with no existing positions, avoiding repeated position opening risks. Both long and short signals include prediction probability annotation for subsequent trade analysis and strategy optimization. Exit logic sets both stop loss and take profit conditions, establishing position risk management. Visualization design fully considers traders' practical needs. Prediction curve uses blue display for easy observation of algorithm prediction changes. Long and short threshold lines use green and red dashed lines respectively, clearly showing signal trigger zones. The 0.5 neutral line provides probability baseline reference. Trading signals are displayed through different shapes and colors on price charts. Long signals use green up triangles. Short signals use red down triangles. Intuitive and clear. Alert conditions include prediction value information, convenient for traders to understand signal strength. This design presents complex machine learning algorithm results in a concise, intuitive way, lowering the technical barrier for strategy use. This strategy's effectiveness highly depends on data quality and market characteristics. The strategy needs sufficient historical data for pattern learning, making it more suitable for mature mainstream coins rather than newly listed tokens. It performs best in relatively stable market environments, as extreme volatility destroys historical pattern validity. Special attention must be paid to overfitting problems. When a strategy performs perfectly on historical data, it may mean the model has overlearned noise rather than true patterns. Different coins have vastly different market characteristics, requiring targeted parameter adjustments. Blind application may cause strategy failure. For new coins lacking sufficient historical data and market behavior patterns, use cautiously or extend observation periods. The key to advanced application lies in establishing parameter adaptive mechanisms, allowing strategies to automatically adjust based on market changes. Meanwhile, feature importance monitoring helps identify the most predictive technical indicators in current market environments, improving strategy adaptability and stability. From a professional quantitative analysis perspective, this KNN strategy demonstrates high standards in both design philosophy and technical implementation. It represents a beneficial exploration of upgrading traditional technical analysis toward intelligence. Strategy completeness performs well, establishing a complete technical framework from feature standardization to KNN prediction. The correction of timing logic issues particularly reflects rigor. Risk management has basic framework but room for improvement. Static stop loss and take profit settings need more dynamic adjustment mechanisms. Adaptability is its core advantage. Achieving intelligent weight allocation for multiple indicators through historical pattern matching. This approach is indeed superior to traditional methods. Understandability is above average with clear code logic but some complexity in machine learning components. Innovation deserves recognition. The combination of KNN algorithm with technical indicators opens new quantitative thinking. In terms of practicality, the strategy design is reasonable, but live trading requires more improvements, including parameter adaptation and abnormal market handling. We must recognize that financial markets' high uncertainty and non-stationary characteristics pose fundamental challenges to any prediction based on historical patterns. This strategy can serve as a quality starting point for quantitative research. I recommend thorough backtesting and optimization verification on the Inventor quantitative platform before building more stable quantitative strategies.